Amazon found that every 100 milliseconds of added latency costs them 1% in revenue. That is $1.7 billion per year for a delay you cannot consciously perceive. And yet, low latency alone cannot save YouTube's encoding pipeline. They process 500 hours of video every minute. That requires throughput. Two different problems. This video covers both. In this video, we define latency and throughput precisely, show you where each one breaks in a real system, and give you a two-question framework to pick the right metric in any interview. Latency is the time from a user's action to the system's response, measured in milliseconds. It is the metric users feel directly. One slow database query can ruin the entire experience. Latency has three components: network round-trip time packets traveling across wires, processing time your server computing the response, queuing delay your request waiting in line while the server handles others. All three add up. Throughput is total volume per unit time, requests per second, megabytes per second. One user sees latency, the whole system produces throughput. You can have a fast system that handles 10 requests per second or a slow system that handles 100,000. These are completely independent axes. The Mumbai-Pune Expressway, your latency is how long it takes you to drive the route. The expressway's throughput is how many cars make the journey per hour. A 2-lane road might be fast but low throughput. A 16-lane highway has high throughput but does not make your individual drive faster. Same road, different metrics, different solutions. Let us trace a single request and count the milliseconds. 3 parties: browser, app server, database. Browser sends the request. Network transit to the data center, 15 milliseconds minimum. You cannot eliminate this. You can only reduce it by bringing data geographically closer, which is what CDNs do. App server queries the database. Disk I/O costs another 20 milliseconds. This is almost always the dominant latency source in web applications. Database returns the result over the private data center network. 2 milliseconds. Response travels back across the internet. Another 15 milliseconds. Total 52 milliseconds. Clean, unloaded system. User is happy. Now put the server under load. 500 concurrent requests. 8 CPU cores. Your request waits 450 milliseconds before even being touched. The actual work takes 52 milliseconds, but the user waited 502. Queuing delay is why systems that feel fast in testing fall apart in production. 1,000 requests per second, single server, CPU saturated, queue fills up, latency spikes, throughput capped by the single machine's resources. Add 2 more servers, load balancer spreads the request, throughput triples, each server runs at a third of capacity. Queue clears. This is horizontal scaling solving a throughput problem. Here is the key insight. Latency did not change. Each request still takes 52 milliseconds. More servers increase capacity. They do not make individual requests faster. These are two separate problems. To actually reduce latency, add a Redis cache. Cache hit returns in under a millisecond. The 20 millisecond database query is eliminated. Latency drops to 32 milliseconds. Servers solved throughput, cache solved latency, same system, different tools for different problems. The design goals pull in opposite directions. Latency first systems optimize each user interaction for speed. Throughput first systems maximize how much work gets done, even if each item takes longer. Latency first systems use CDNs, Redis caches, and pre-computation to answer quickly. Throughput-first systems use Kafka queues, batch processors, and parallel worker pools to handle massive volume. Stock trading, sub-millisecond latency required. A 10 millisecond delay means executing an order at the wrong price. ML training pipelines, no user is waiting. Processing a million records over several hours is perfectly fine. High throughput is the only metric that matters. Most mature systems need both, but they separate concerns by path. The user-facing read path is latency critical. The background write path is throughput critical. You route each type of work to the right architecture. This is how Swiggy, Hotstar, and Razorpay are actually built. Full system trace, user clicks, latency clock starts. CDN, edge node, geographically close to the user. Static assets served in under 5 milliseconds. Latency optimization 1. Load balancer spreads API requests across the server fleet. Throughput optimization 1. No single machine takes the full load. Redis cache, result returned in under a millisecond. Database query bypassed. Latency optimization 2. Writes are queued asynchronously. User gets an instant confirmation. Database commit happens in the background. Throughput optimization 2. Decoupled from the user facing path. Result, users see responses in 20 milliseconds. System handles 50,000 requests per second. Two metrics solved independently. In the same architecture, the optimization question comes in every system design interview. Here is a two-question framework that always works. Is a human watching a loading spinner? Latency is your metric. Optimize for under 200 milliseconds. Is a batch job or another service waiting? Throughput is your metric. Optimize for maximum volume per second. Find the bottleneck before you optimize. Network distance, use a CDN. Compute saturation, add horizontal servers. Database I/O, add a cache for reads, a queue for writes. Never optimize blindly, measure first. The answer that will distinguish you in any senior interview. Separate concerns by path. User facing reads are latency critical. Serve from CDN and cache. Background writes are throughput critical. Use async queues and batch workers. You do not choose one metric globally. You choose per path. That is latency versus throughput. Latency is the time for one request. Users feel every millisecond. Throughput is the system's capacity. The business lives and dies by it at scale. Separate the paths, solve each independently. You can now explain both metrics precisely. Spot queuing delay as the hidden culprit. Apply the two-question framework in any system design interview and separate the paths, the pattern behind Swiggy, Hotstar, and Razorpay at scale. Next, video caching. We have mentioned Redis caches several times. Now we go deep. How does Redis actually work? Cache aside versus write through. When do you use each eviction policies? LRU versus LFU. Link in the description. Subscribe to ByteLearn for one concept per week. Under 8 minutes, interview ready. Hit the bell. See you Wednesday. Which part clicked for you? The three components of latency, the Mumbai-Pune expressway analogy, the queuing delay spike, or the layered architecture answer. Drop it in the comments.